Okay, so in our last video we ended with finding horizontal asymptotes and me giving you this kind of so-called bubble theorem. It's kind of a made-up thing, but it helps you visualize perhaps a way where you can quickly identify what the horizontal asymptotes are. All right, so uh, when we look down here at this last example on our third page in our notes, it says finding an horizontal or oblique asymptote. So I crossed off oblique asymptotes. I would rather us focus on an end behavior model for anytime we don't have a horizontal asymptote. So in this case, we notice that the degree in the numerator, so the numerator degree, numdeg, numerator degree is a 4, and the denominator degree, so we got to identify first, is a 3. Okay, so clearly the numerator has a greater degree than the denominator. So all I want you to do for those kinds of problems is to circle once you have to have the numerator and the denominator each in standard form. So if you see factors up there, multiply out the factors, get the circle the highest degree term in the numerator, and our end behavior model is going to be our highest degree in the numerator term divided by the highest degree term, the whole thing, coefficient, x, and the exponent. The highest degree term in the denominator, then you're going to cancel. So x cubed, you can cancel. So if you think about this as being multiplied together 3 times, and up here you have x multiplied together 4 times, you can cancel 3 of the x's up on top and all 3 of the x's on the bottom, and all we're left with in the numerator is 3x, and we're not left with anything in the denominator. So basically, we can rewrite this fraction with our using an end behavior model, and we would say, okay, our end behavior model is y equals 3x. That means that when we're graphing this function, this y equals 3x, that would look like that, would be a slope of 3 going through the origin. That would kind of be like an oblique asymptote. Kind of like an oblique would be kind of like a diagonal asymptote. But the bottom line is the graph will approach that asymptote from one side or the other, and that's what we're concerned with. We don't have any horizontal asymptotes, but we do have kind of a direction that the graph is going to go, either to the when x gets really, really big in the positive direction, or when x gets really, really big in the negative direction. It'll approach positive infinity to the right and negative infinity to the left, and we just kind of use that end behavior model to show where the graph is going for large values of x to the right as well as large values of x to the left. Okay, so let me actually have you guys do one here. I'll pause the video for you. Y equals 4x to the third minus 2x plus 1 all over 3x plus 5. So I want you guys to find me, don't find the oblique asymptote, but you would be asked what's the horizontal asymptote or the oblique asymptote. Whenever you're asked that, I want you to find me an end behavior model. Okay, so go ahead and answer that question right now, and you should have already answered the question and chosen y equals, we're going to circle 4x cubed and we're going to circle 3x, and we're going to write 4x cubed over 3x, which simplifies to 4/3 x squared, because 1x cancels there and you subtract 1 from that exponent and we get 4x squared over 3, or 4/3 x squared. So that's our end behavior model, y equals 4/3 x squared. All right, so let's take a look at the back side. All right, find the horizontal or oblique asymptotes, if any, of the graph of r of x equals 8x squared minus x plus 2 over 4x squared minus 1. All right. So you should have already tried to answer that, and if by chance you got the wrong answer, then you can rewind the video and go back and answer it correctly. But if you remember what we said, we have the same size bubble top and bottom. The degree in the numerator is a 2, degree in the denominator is a 2, they match. So then we peel off the coefficients, So our horizontal asymptote is y equals 8 over 4, but better to write y equals 2. That's it. That's all you have to do.